Let's talk about how we can use proportions and similar triangles to solve real-world problems. For example, a surveyor is measuring the width of a highway using similar triangles. He's found the following measurements, and we need to use that information to help him calculate the width of the highway. Similar triangles can be a great way to measure things that aren't safe or aren't possible to measure in the real world. For example, it's probably not very easy to measure the width of a highway because of, the cars. So instead, we can find these measurements of similar triangles and use them to calculate the width of the highway safely. These two triangles are similar triangles. They both have right angles. Right angles are congruent. And these angles are vertical angles. So by the angle-angle similarity theorem, we know that these two triangles are similar to each other. So we can set up a proportion to relate their corresponding side lengths. First, I'll write x, which is the longest side of the bigger triangle, and I'll put that over top of 45, which is the shorter side of the bigger triangle. So now I'll write a ratio that goes in the same order for the smaller triangle. Longest side over shortest side. And then I'll cross multiply and solve. 18 times x is 18x, and 45 times 24 is 1080. Divide both sides by 18, and we find out that the highway has a width of 60 meters. Next up, we're going to calculate the diameter of a nuclear cooling tower. Obviously, we can't get inside of a nuclear reactor to measure its diameter, so we have to find a safer way to figure out that measurement using geometry. So this inspector has set up this diagram, found these measurements based on the cooling tower. This is like a top-down diagram, so you're looking from the sky down on top of the nuclear reactor. And what we need to calculate is the length of x, which is the diameter of this circle. There are two similar triangles in this diagram. This little baby triangle over here is similar to the entire triangle. They share this angle by the reflexive property it has to be congruent to itself. And we have a bunch of corresponding angles that are congruent to each other because these two lines are labeled as parallel. So since I have similar triangles, I can set up a proportion to solve for the missing side lengths. So I'll write x on top, that's the diameter which we're trying to calculate, and I'll write 25 on bottom, so that's comparing the two kind of vertical lengths. And I'll set that equal to 104 plus 40 over 40. Many of my students write 104 over 40, and that's not correct. 40 is the length of this side of the smaller triangle. 104 is not the entire side length of the big triangle. It's just part of it. You need to add and find the entire length of this side of the big triangle so that it's actually corresponding to the length of 40. 40 is a side length, and 144 is a side length. Then we'll cross multiply. So I have 40x equals 3600, which means x equals 90. So the cooling tower has a diameter of 90 meters. And our last problem is a classic triangle similarity word problem. You will see this kind of a word problem in literally every math textbook ever. And it all has to do with measuring the height of something that's really tall using shadows. So I have the shadow of the flagpole, and I have the shadow of the person. And those two shadows line up with each other. The tip of the shadow from the person is the same as the tip of the shadow from the flagpole. So let's read and figure out what our measurements are. Tanea is going to measure the height of a flagpole. She is 5 feet tall, and she measures the length of her shadow to be 1.5 feet long. Pause. Let's go ahead and write that on the diagram. She's 5 feet tall, and her shadow is 1.5 feet long. And play. She measures the length of the flagpole shadow to be 7.5 feet long. She lines up the edge of her shadow with the edge of the flagpole shadow. So let's label that on the diagram. If the flagpole has a shadow that's 7.5 feet long and it ends at the same place as her shadow, then I can say that this length right here is 7.5 feet long. And the only thing that I don't know is the height of the flagpole. These two triangles are similar triangles, this little baby triangle created by Tanea and the big triangle created by the flagpole. They're similar triangles because they share this angle right here, so by the reflexive property they have to be congruent angles. And, assuming that the flagpole was built correctly and that Tenea is standing up straight, each of these things make a right angle with the ground. They're perpendicular to the ground. So these right angles would be congruent as well, so by angle-angle similarity, these two triangles are similar. So since I have similar triangles, I can set up proportions to solve. So I'm going to write x over 5. So that's the height that I'm looking for, the height of the flagpole, over Tenea's height. And set that equal to the length of the shadow of the flagpole over the length of the shadow of the person. So then I can cross multiply. 1.5x equals 37.5, and I get an answer of 25. The flagpole must be 25 feet high. And that's all you need to know about applying proportionality and triangle similarity to the real world. In our next lesson, we're going to be discussing what a midsegment of a triangle is and how that relates to similarity.